In this video, we will discuss the factorial and gamma functions in Python. We'll first go through what a factorial is and how it can be calculated manually. Then we'll discuss how the math.factorial function works and some of its limitations, perhaps most notably that it will only work for a positive whole number. We'll then cover what the gamma function is in the math module and how it fills in some, though not all, of those limitations. And we'll close by touching on a different gamma function from the scipy library, which can take you to the next level and can handle just about any number. As always, timestamps are in the description if you'd like to jump around. So let's dive right in with an explanation of what a factorial is for positive integers. For a positive integer n, the factorial is the product of all the positive integers less than or equal to n. What does that mean? Well, for example, 3 factorial is 3 times 2 times 1. So 3 times 2 is 6, times 1 it'll still be 6, and indeed 3 times 2 times 1 is 6. And then 6 factorial, it's the same thing. It's 6 times 5 times 4 times 3 times 2 times 1, okay? So we have 6 times 5 is 30, 30 times 4 is 120, 120 times 3 is 360, 360 times 2, so all these numbers times 2 is 720, and then 720 times 1 is just still going to be 720. And that was awful. You see how tedious that was? How boring that was to even listen to? How easy it was to make a mistake? I almost had a couple typos in there just typing it in, and that's just with 6. What if we were asking about 100 or 100,000? Well, the nice thing is that we don't have to do that whole long process. We can express the same question by asking, what is 6 factorial, and get our answer. And we can do that with the math module's factorial function. Just import math, and then we can do math.factorial, and inside these parentheses we put the number whose factorial we want to find. In this case it was 6, and there it is, the 720 that we got before, but this time instead of having to type 6 times 5 times 4 times 3 times 2 times 1, we were just able to do it all in one fell swoop with math.factorial, and then in the parentheses 6. There it is, 720. And notice these numbers are going to be getting really, really big. By the time we get to math.factorial of 10, it's already 3 million and change. What about 100? Okay, look at this. It's an enormous, enormous number. Okay, just huge. What if we did, just to say, as an example, 100,000? Now, my computer can do this, but it's not going to be happy about having to do it. And let's just see how long it takes to even compute this. It's still going. Still going. Hasn't finished yet. Still waiting to spit it out. It's going to be a really big number. And here it is. Okay, and look at this. Look at this. And it just goes and goes and goes and goes. Here's my scroll wheel down here. Oh my goodness. Okay, it's a beast. It's a beast. And so of course these factorials can get really, really big. And you know, you might also have previously learned in math class that the factorial of 0 is 1. See, math factorial 0 is 1, and there's several justifications given for this in mathematics, but between you and me, it's really just a convention, and Python does follow that convention. You can see this math factorial of 0 does give you 1. There's lots of reasons behind this, behind why we say math factorial of 0 equals 1. Having to do with arranging things and other, you can certainly research that. There's many videos explaining the different justifications for that, so I won't get too into it. So definitely something to look at if you're interested, but just for our purposes, just know that math factorial of 0 does equal 1, both by convention in mathematics and, of course, in Python as well. So here's the key limitation to math.factorial. By definition, it's not going to give you any output if you feed it a negative number or a non-integer. Okay, so here's a graph of just the first handful of numbers when y equals math.factorial of x, and I just made this in matplotlib, and you see there's a pretty limited world of values here. We're just getting responses to our question when the x is a positive integer, 0, 1, 2, 3, 4, 5 in this case, and we're only getting these positive integers in response, okay? And that all makes sense. You know, given what we know about what math.factorial gives us, it's only going to give us positive integers. It's just going to say what's 5 times 4 times 3 times 2 times 1, and then plot it. It's 120, okay, and we see math.factorial of 5 is in fact that 120, and so it all checks out. But wouldn't we like to know what numbers come between these points? What numbers are between all of these points? Well, there's an infinite number of lines we can draw, right? You know, you can draw straight lines between the points, you can draw lines that, you know, double back and make a loop-to-loop and then connect with the points, right? You can draw anything, but what we want is a nice curved line that is the best fit for how we can connect these points and this nice curved best possible fit. And in fact, mathematicians have done this, and the answer they came up with is the gamma function. And as we see in this next graph, we can use the gamma function to draw a curved line between these points. And we'll return to this graph, but the gamma function is a fairly complicated function. So first, I'll show it to you in all its glory, and then I'll try to make it a little bit simpler, especially for those of you who are looking at this and say, it's all Greek to me, almost literally, right? Because it has Greek letters. As you see, the gamma of x equals the integral from 0 to infinity of t to the power of x minus 1 times e to the negative t dt. And a lot of you watching will know exactly what this means, but if it sounds like I just said a bunch of word salad, have no fear, because for purposes of this video, what we need to know is that n factorial equals the gamma of n plus 1. And remember that by definition, n factorial, and you know, when you write it by hand, factorial has this exclamation mark. That's not the case in Python because the exclamation mark's already taken by not. But you know, n factorial by definition can only be a positive integer, because that's what a factorial, that's what this exclamation mark signifies. But the good news is that the actual gamma function up here also works for numbers that are in between the points that we saw before, and so we can extrapolate that out in this lower equation in the same pattern. So for all intents and purposes, we can consider this second equation, at least for purposes of this video, to be correct for all numbers, and you'll see it will return our curved graph. You know, so to return to our curved graph here, if you see the equation that we plugged in, y equals math.gamma of x plus 1, where before our n factorial only worked with whole positive numbers, and that's where we have all these blue triangles. Here we see that the gamma of x plus 1 is going to give us the factorial of what any of those numbers would have been had we been able to take it. You know, why plus 1? Why can't we just say, you know, math.gamma? Well, there is a function like that, but not in Python, not in the math module in particular. So what we do have in the math module is gamma. And why do we need to do the plus 1? If we go back here, we'll see there's an x minus 1 in our function, so we do need to correct for that, basically, by having this n plus 1 here instead. So we're going to be thinking of this in terms of math.gamma of x plus 1. So let's go back to Python, and we'll see it in action by plugging in some examples. So we know that n factorial is math.gamma of n plus 1, right? So let's ask, what's the factorial of 4? Well, it would be math.gamma of 4 plus 1, right? So And that's really the same thing as asking what is the factorial of 4. And you see it's 24.0. Notice that the gamma here is giving you a float value, whereas before this factorial gave you an integer value, so that's just one thing to keep in mind. But this should be the same thing, right? Math.factorial of 4 is 24, so working great. Now, the whole point though of using this system is not to use these whole positive integers, right, but rather to ask, for something more like a decimal or something in between. So let's do something a little spicier. Let's do math.gamma of 0.3 plus 1, and we get an answer. It's 0.897 and change. So if we just go to our calculator that comes with our computer and ask it, hey, what's the factorial of 0.3? So 0.3 and then factorial, and there it is. It's exactly what we wanted. So 0.3 factorial and math of gamma 0.3 plus 1, same thing. And this is not a mathematic proof. This is just a double check under the assumption that the good people at Microsoft who made the default calculator that comes with Windows 10 know what they're doing. And so in any event, so this math.gamma 0.3 plus 1 gets you that factorial of 0.3, working great. And how about some negative numbers? Could that curve that we saw before continue into negative space? Well, yes and no. If we do math.gamma of, say, negative 4.3 plus 1, yeah, we get an answer. So this is the factorial of negative 4.3 as far as extrapolating it with this gamma function is concerned, so that's good. But what about just math.gamma of, negative 4 plus 1? What's going to happen? Value error, math domain error, it doesn't work. And in fact, the gamma of 0 or the gamma of any negative integer with this math.gamma, so math.gamma of 0, math.gamma of negative, some integer, is always going to give you this math domain error. Why? To make a long story short, when we put a 0 or a negative integer into our math.gamma function, the result would have to include a division by 0, which we all know can't happen. So the math.gamma won't do it because it's technically not possible within the actual mathematical gamma function, because it would require a division by 0. And that makes sense, but it can lead to some big headaches if you're using something like an array of values. So the last thing that I'll show you is one final way to take the gamma function, and that's with scipy. And a key advantage to you doing the gamma function with scipy is that instead of just throwing you an error when you ask for the gamma of 0 or a negative integer, instead it'll just say the answer is quote-unquote infinity. So the nice thing is if you're feeding their computer a big range of values, you won't get tripped up with a bunch of errors every time it hits a negative integer or 0. The computer will just say, it's infinity, and then kind of just move on. So if you don't have scipy already, you can probably install it by going to your command line, and I'll just show you with the terminal that comes with PyCharm. And so here, if you do it, you can type pip, P-I-P, install, and then scipy, S-C-I-P-Y, and then just hit enter. And it'll tell me I already have it, requirement already satisfied, because I already have scipy installed. But if you don't, then that should work for you. If it doesn't work for you, then we'll certainly put a link to scipy's website in the description, and there will be much more detailed instructions there. So scipy has these quote-unquote special functions, and just a ton of them. But we're only going to use one, and that's gamma. So we can say, in our first line of our little program here, we'll say from scipy.special import gamma. And note that we're actually typing in the special here from scipy.special. Scipy is really, really big, and if you just say from scipy import all, like you might with some other things, it won't import these special functions. So it's important to actually write from scipy.special, and then we're going to import gamma, and then we can just call it gamma, because that's what we imported it as, so to speak. And so, all right, now we have our gamma function from scipy. Let's try it out with print, and let's make this a little bigger, with print gamma of 3 plus 1 or something. Okay, and then let's run it, and there it is, 6.0. And so looks great. All right, so and of course that's 3 factorial, as we saw at the beginning of the video, is going to be the same as the gamma of 3 plus 1. Good. And so now let's do gamma of 2.4 plus 1, just to see it in action, and we'll run it, and there it is, it's 2.98 and change. And just to make sure we're on the right track, we can bring it up on our calculator as well, just as a quick double check, and that's 2.4 factorial. Looks great, 2.98 and change. Wonderful. All right, and finally, the reason that we're here, negative numbers. All right, so let's try it out. Gamma with scipy now, gamma of -4 plus 1. Let's run it. Infinity, inf, which we saw in our constants video. It's a float value of infinity, and it's not giving us an error, it's giving us an answer, it's giving us infinity, and the same will be true with, what if it's, something that would lead to being the gamma of 0, which would be -1 plus 1. Let's try that. Also infinity. Okay, great. And so when we plot this out on one final graph that I'll show you, we do see that these whole negative numbers do go up to infinity, and that's how scipy does it and represents it. We could perhaps more accurately say that there shouldn't be any lines here at all because we can't divide by 0, but the good news is that we do have these negative values, these little curves here, which is great. And so we can plot a range of values. And if you're curious how I made this with matplotlib, just a 3-second explanation. I made a list of x values to be numpy's linspace function, basically said, hey, make my x values, I think I used 500 numbers between -5 and 5 spaced evenly, which would have given me a lot of headaches had I used math.gamma, because it can't read something like that, because every time it hits one of these negative integers or 0, it's going to throw you a math domain error, and so it would have given me a lot of headaches. It would have been much harder to use. But the scipy special gamma, scipy.special.gamma, which we just imported, as you saw, as the word gamma to make it a lot easier, can do it no problem. And just as before, we had our factorials here. We still do in this first quadrant. All these blue triangles are factorials, looking great. All right. And I actually used the scipy factorial function, which is also in the special value. It's the same way we imported gamma. You would just import factorial instead. Okay. And that's it for this video on the factorial and gamma functions in the math module, also discussing the gamma function in scipy at the end. Thanks very much for watching.